Morning, everyone. Morning, everyone. Come on in. Questions while we wait? If not, maybe I'll give you a question that has to do with what we were doing last time. Morning, everyone. Come on in. How are we doing with the material? Why don't I start you off with the following? Oh, did it say 1:30? I must have just pressed on 0 instead of 9. Sorry about that. Morning, everyone. Questions? Why don't we, while we're waiting for others to come in, why don't we discuss this question here, which has to do with what we were looking at last week, concept of continuity. And what's the point? For values bigger than 3, regardless of what A and B are actually going to be, for values bigger than 3, this is going to be a polynomial. So regardless of what A and B are, this part is continuous. Similarly, for values between 2 and 3, again, regardless of what A and B are, this is going to be a polynomial. So continuous there as well. And here you've got a rational function. And we know that rational functions are continuous in their domain. So everywhere except at -2, this function is continuous. So in particular, for values less than 2, did I say -2? I meant 2. Everywhere except 2, this function is continuous. So for values less than 2, this function is continuous. So the only place we need to worry about f being continuous is where it goes from one piece to the other. So immediately, f is continuous. Everywhere, except perhaps at x equals 2 and x equals 3. This is the only place you need to worry about continuity. Everywhere else, you know you're good. Michael has a question here. You can solve that question without L'Hopital's rule. Well, in fact, I don't know. I don't know that to be true. I don't know that to be true. What would I do here? You can it's math 139. I mean, there's no way for me to change it now. Unless we stop this stream and we start another one. So let's not do that. Yeah, so I would have suggested sum and difference identities for sine and cos, but that's going to give you a, well, wait a minute. You're saying tangent, right, yeah. Okay. Yeah, so I would have maybe suggested sum and difference identities. Play around with those. See what happens. Will epsilon delta be on the midterm exam? We still have not completely decided that. We'll see. Try sum and difference, Michael. This is to answer Michael's question. Try sum and difference identities for cosine. You've got cosine of 2x minus 1/2. So cosine of a minus b kind of thing. Play around with that, as well as maybe cosine 3x kind of thing. So this function immediately, without doing any work, well, I mean, apart from a small argument, is continuous everywhere except perhaps at 2 and 3. So now let's force it to be continuous at 2 and 3. Let us evaluate the limit as x goes to 2 from the left. And for values less than 2, your function is this. X squared minus 4 over x minus 2. And if we just blindly plug in, we get a 0 over 0. So let's factor that. If you factor this, x minus 2x plus 2, over x minus 2, these cancel out nicely. And this just gives us a limit of 4. If you consider the limit as x goes to 2 from the right, values close to 2 but bigger than 2, the function is ax squared minus bx plus 3. And as x goes to 2 from the right, this is just a polynomial, so you know you can plug in. This is 4a minus 2b plus 3. And that is also equal to f of 2, right? When x is 2, you're plugging it into this. So for continuity at 2, we need these two limits to be equal. 4a minus 2b plus 3 has to be equal to 4. Or 4a minus 2b has to be equal to 1. Willem, what are you asking here? Why is this limit equal to that? That's because it's a polynomial. So you know you can just plug in that's property 10. Limit law 10. Okay, one of those limit laws, number 10. Tells you that when you have a polynomial, you can just plug in. This is also, why is that true? That's true because polynomials are continuous. Similarly, let's look at the limit as x goes to 3. And for values less than 3, the function is this. And limit as x goes to 3 from the left, again, it's a polynomial. So same thing. William's asking why I'm plugging in 4. I'm not plugging in 4. I'm making it equal to 4. I'm not sure. Not sure what you mean here. I'm not plugging in 4. I'm plugging in 2. Very good. And again, polynomial, you know to be continuous, so we can just plug in. And what do we get? 9a minus 3b plus 3. Similarly, limit as x goes to 3 from the right. For values bigger than 3, the function is, for values bigger than 3, the function is 2x minus a plus b. And once again, it's a polynomial. So we can just plug in. And this is 6 minus a plus b. Which, again, by the way, this is equal to f of 3, right? Say a condition of the continuity business, right? Because in the definition of continuity, you need the limit from the left to be equal to the limit from the right, but also to be equal to the function at the point. So for continuity, we need these 3 things to be equal, which really boils down to these 2 things. 9a minus 3b plus 3 should be equal to 6 minus a plus b. If you bring the a's and b's to the other side, this is 10a minus 4b is equal to 3. Ali is asking why are we taking the irrational function when doing the limit to 2. We're checking for continuity at 2 and at 3. We're really forcing continuity at 2 and 3. Definition of continuity at 2 is that the limit from the left should be equal to the limit from the right, should be equal to the function at 2. But for values less than 2, it's the rational function. So that plays a role in continuity there. And there you have it, right? I mean, 2 equations, 2 unknowns. 10a minus 4b equals 3, and 4a minus 2b equals 1. You can solve that using matrices or otherwise. Right, 2 equations, 2 unknowns. Solve however you want, whatever you want to do. If you want to solve two b is equal to 4a minus 1. So if you multiply, if you multiply this whole thing by 2, you get 8a minus 2 is equal to 4b. But you've got the 4b right there. So if you plug that into there, we get 10a minus 4b, which is 8a minus 2. The whole thing is equal to 3. Open up the brackets. 2a plus 2 is equal to 3. So a is easily seen to be 5 over 2. And 18b. B is 9 over 2, is that correct? That doesn't seem correct. What have I done here? It's 20 minus 2 is 18. It's 18. Yeah. Why isn't it working? It's 25 minus 18. That's not 3. That's where have I made the mistake? It's 1/2, not 5 over 2. 1/2, thank you. Thank you, there it is. There it is. And consequently, 4 minus 2 is 2. So b is 1/2 as well. Let's see if that is better. 5 minus 2 is 3. Looking good. And 2 minus 1 is 1. There it is. Very good. Very good. Very good. Thank you. There it is. So if a is 1/2 and b is 1/2, your function is now continuous. How are we doing here? Questions? Let's consider an important theorem related to continuous functions. Well, Guillaume is asking, why do we want to know if a function is continuous? Consider this important theorem known as the intermediate value theorem. Which says that let f of x be continuous. On the closed and bounded interval AB. Meaning that f is continuous at every point in the interval. and let k be a real number, be between f of a and f of b. Then there exists a c in the open interval AB such that f of c is equal to k. Let's illustrate what is happening from a graph point of view. From a graph perspective, let's observe what is happening. We have a function that is continuous on the interval AB. So we can graph it B between. So we can graph the function without lifting the pencil from the paper. So this point is f of a, and this height is f of b. What the intermediate value theorem says is that if you choose any point in between f of a and f of b, if you choose any point k in between these two, then there exists a point c such that f of c is equal to k. Pretty clear from the graph, right? It says any point in here, there has to be an intersection here. Any horizontal line between f of a and f of b is going to have to meet the graph. I'm offering this without proof, only because the proof is rather technical and doesn't really bring anything more to the understanding. But let's take an example. Here's a nice example. Consider this polynomial, x cubed plus x squared minus 3x minus 1. I claim that this polynomial has a real root. I claim there's a point where this polynomial is equal to 0. There's a value of x you can plug in which will make this function 0. Well, you try a few values and it's not working. You can't seem to find the root, but it doesn't matter. We can still prove there is one. What do we know? P of x being a polynomial is continuous on the whole real line. This function is continuous everywhere. if you plug 1 into the function, what do we get? P of 1 is -2. Absolutely, thank you. What about P of 2? P of 2 is 8, plus 4 is 12, minus 6 is 6, minus 1 is 5. Thank you. And there you have it. By the intermediate value theorem, since 0 is between -2 and 5, there exists a C in the interval 1 to 2 such that P of C is equal to 0. C is your root. Danielle is asking the obvious question, why did we choose 1 and 2? Is it just random? Of course it is not. We chose 1 and 2 because it worked here. What does that even mean? Well, according to the intermediate value theorem, we wanted to show the function was 0 somewhere. Right? We wanted to show the function was equal to 0 somewhere. So we chose a point where the function was negative, and we chose a point where the function was positive. The polynomial is continuous in the interval 1 to 2. So you can graph the function without lifting the pencil from the paper. And the only way to get from -2 to 5 is by crossing the x-axis somewhere. And that is your point C. That is your root. Could we have chosen the interval 1 to 3? Right? If x is 3, we get 27 plus 18 minus 9. So 27 plus 9 is 36, minus 1 is 35. So that would have worked as well. Absolutely. The interval would have been larger. So not as good, but still the conclusion would have been the same. This, of course, as Matthew points out, this does not work if the function is not continuous. The theorem requires continuity of the function. Exactly that. Let me point out, if we may, that this intermediate value theorem, in this context, it's sometimes referred to as location of roots theorem, right? Because you're locating the root. Here you're finding a root between 1 and 2. You're showing that there exists a root between 1 and 2. We can use successive iterations of the intermediate value theorem to approximate what the root actually is, right? Because, you're looking at this and you're thinking to yourself, I cannot come up with a number, x, such that if I plug in x, I get 0. We know one exists between 1 and 2. Let's split that up right down the middle at 3 over 2. And plug in 3 over 2. Sophia's asking what happens if you were to choose a value that made P of x 0. Then, it's a jackpot there. That's what you were looking for. So if you have that, you're good to go. Chances are, though, the question is probably made up so that that's not going to happen. But if it does, it's over. What if it bounces off the x-axis and never crosses it? Well, good point. Then, this process breaks down. So, it's not like the intermediate value theorem is something so incredible. Matthew has worked it out for us. Thank you. Matthew has worked out that P of 3 over 2 is 1 over 8. Thank you for that, Matthew. Conclusion. At 1, you were at minus 2. At 3 over 2, you're now at 1 over 8. So you know that the root now has to lie in the interval 1 to 3 over 2, right? You had started with a root in some interval of length 1. You've already cut it down by half. You already know that the root has to be in the interval 1 to 3 over 2. Somebody's asking if we could have used 1/2. The idea is, well, wait. In this situation, no, you don't want to go outside the interval. You already know there's a root in the interval 1 to 2. Who knows what's happening outside of that? But you see what's happening, right? We've cut down the interval by half, and now, either the root happened at 3 over 2, or it had to happen in one of these two things. If this one was bigger than 0, it happens in this interval. If it was less than 0, then it would have happened in the interval 3 over 2 to 2. So either, three things can happen. Either the 0 is exactly at 3 over 2, or it's in this interval, or it's in that one. Now it's in here, and you can repeat. Cut that down by, look at exactly the midpoint, which is 5 over 2. 5 over 4, sorry, 5 over 4. And look at your function at 5 over 4. Is this bigger? Well, first of all, is it 0? If it's 0, that's your root. If not, it's either going to be bigger than 0 or smaller than 0. So if it's bigger than 0, there's a root in here. And if it's smaller than 0, there has to be a root in here. Does anybody work out what P of 5 over 4 actually was? Minus 79 over 64. Thank you. So it's negative, which means your root is in the interval 5 over 4 to 3 over 2. So you see, by successive iterations of the intermediate value theorem, you had started with an interval of length 1, and you now have an interval of length 1/4. And you can keep on doing that to get a better and better approximation. Somebody's asking, how small does the interval have to be? And then Sean wants to know what the root actually is now. And then, that's the issue. Who knows what the root actually is? Well, I say that. Interestingly enough, what you have here is a polynomial degree 3. If you had a polynomial degree 2, right, ax squared plus bx plus c, you could find the roots using the quadratic formula. Right? Quadratic formula will give you the roots of a quadratic polynomial. This is a cubic polynomial we're working with. Some of you may be interested to know that there actually is a formula very much like the quadratic formula. It's called the cubic formula, as you might expect. And it will give you the actual roots of a cubic equation. Quadratic formula, the formula is very simple to remember. Cubic formula, the formula will take up the whole board, whole line of the board. So it's not something anybody remembers. Thank you for that, Benjamin. And, well, I mean, you know, you wrote that down. Here's my question to you. Is that just an approximation? Does the decimal keep going forever? So is it a rational number, or is it an irrational number? Those are excellent questions. Does the decimal repeat at some point, or does it continue on without ever repeating? Those are all nice questions. And yeah, so there is a cubic equation which will take up one line of the whole board, so nobody remembers it by heart. But this idea, without using anything, you can keep approximating very, very nicely, breaking up the interval into halves always, and getting a better and better approximation. Somebody mentioned Newton's method. Newton's method is something slightly different. Maybe we'll discuss it later on. Questions here? Do we want to do one more example of this? What class would you learn the cubic form? You know what? You don't. You don't. There is no class that will teach it to you. But luckily, we live in the information age, and if you Google cubic formula or cubic polynomials, I'm sure it will give you the equation very quickly. Let's do one more. Show there exists a solution to ln x equals x minus square root of x and the interval 2, 3. Right? So many ways to tackle this. Why don't we redefine this by bringing everything to the other side, showing that there's a solution to this is equivalent to showing that this is equal to 0 for some value in in the interval 2 to 3. So if we define the function f of x as ln x minus x plus root x, all we have to do is show that this function is equal to 0 in that interval. But you know the ln function is continuous for values bigger than 0. You know the square root function is continuous for values bigger than 0. And you know that the function x is continuous everywhere. So these three together, this is continuous on the interval 0 to infinity. So in particular, on the closed interval 2 to 3. What is f of 2? Well, that's where a calculator comes in now. So I don't know what that is. Ln 2 minus 2 plus root 2. Whatever that is. Anybody working that out for us? We did not find out if we were going to be tested on epsilon delta yet. We're still discussing that. F of 2, we're saying 0.107. Excellent. What about f of 3? Right, earlier we were using round brackets, now we changed to square brackets. Somebody want to address that? Negative 0.169, thank you. So 0 is between these two. And consequently, there exists a C in the interval 2 to 3 such that f of C is 0. Exactly what you wanted to prove. How are we doing? Everybody with us here? Why am I going from round brackets to square back to round? Look at the intermediate value theorem. In the intermediate value theorem, if your function is continuous on the closed and bounded interval, then there exists an element in the open interval. Right? So to get the answer in here, you had to have started with this to begin with. Such that. You know the only graded assignments are web work, right? Exactly that, Jacob. If somehow it happened that f of 2 and f of 3 were not of different signs, then you would have to keep searching for values somewhere in the interval 2 to 3. And that actually does happen in the book. They're kind of tricking you, but you have to be smarter. All right. Why don't we consider one last example here before we move on? Here's a nice midterm type of question. Let me give you a minute to think about it. That's not, it's always saying if 0 is in between f of 2 and f of 3, I don't think it would be between any other points between 2 and 3. Wow. I mean, let's consider this function. Right, this function which starts off at 4 and ends off at 4. It actually takes on a whole range of numbers between these. Right, I mean, you don't want to restrict your attention to starting and ending points. The function may get outside of that range. It's just that the intermediate value theorem does not guarantee that it does. It may or may not. All right, consider this. We want to show that this function is continuous everywhere. Very nice midterm type of question. What are you doing? The function, so let's discuss what answer we'd be looking for. 1 over x is a rational function. So it's continuous everywhere. Except when the denominator is 0. JD is asking how would we know to check for other values? But I mean, it just depends on what the question is asking. Right, so if the question was telling you that there were values where the function is 0, but the intermediate value theorem does not immediately help you, then you want to adapt. That's all I'm saying. And Michael is asking if that's a hint. Let's not read too much into it. I'm just saying it's an important question that you should know how to do. 1 over x is a rational function, so it's continuous everywhere. Sine of x is continuous everywhere. So the composition is going to be continuous everywhere except 0. X to the 4 is continuous. Everywhere. So the product is continuous everywhere except 0. And this is exactly your function everywhere except 0. So immediately, f is continuous. Everywhere except possibly at x equals 0. The only place you need to worry about continuity is at 0. Is everybody comfortable with that? Questions here? So let's check for continuity at 0. We have to check for the limit from the left and the limit from the right, but to the left and to the right of 0, it's the same function. So there's no need immediately for me to break it up into left and right-handed limits. It's the same function on both sides. If one of the components were not continuous on R, how would the intervals change? Well, I mean, it would depend on how the function would actually have been defined. JD hasn't seen this notation before, so it's R minus 0. Everything except 0. It's like minus. So some books actually have a minus here. Not a fan of that, but I know some books use it. So it's like an except. Ali is asking why we're using sine, or why we're using this when it says not equal to 0, but that's exactly what a limit is. It's the behavior of your function as you get closer and closer to 0 without actually ever reaching it. So we are looking at how this function behaves for values close to 0, but never actually reaching it. And this is the function for values very close to 0, but not equal to 0. So this is the limit we have to evaluate. And as x goes to 0, this part goes to 0, But what is happening to 1 over x? The limit as x goes to 0 of 1 over x is either going to be positive infinity or negative infinity, depending on which side you're looking at. And sine of infinity or sine of infinity does not exist. So this is going to be does not exist, and this goes to 0. So you're looking at a 0 times does not exist. What are you going to do? Does the limit not exist and we're done? And the question was actually wrong? Exactly that, thank you. Squeeze theorem it is. You know that sine of theta is between -1 and 1. So sine of 1 over x is going to be between -1 and 1. If we multiply the whole inequality by x to the 4, x to the 4 being positive, the inequality is maintained. And we have this. As x goes to 0, right-hand side goes to 0, left-hand side goes to 0, so the stuff in the middle goes to 0 by the squeeze theorem. So we have just shown that the limit is 0. In other words, limit from the left and limit from the right are both 0. And finally, what's the last condition for continuity at 0? We need the limit from the left to be equal to the limit from the right to be equal to f of 0. I've rubbed it off now, but by definition, f of 0 was 0. So all the conditions for continuity at 0 have been met. The function is continuous at 0. The function was continuous everywhere else, and so the function is continuous on the whole real line. How are we doing? Questions here? Anybody? We're good? Moving on? How do we know to use the squeeze theorem? Well, you've seen this situation before. 0 times does not exist. Squeeze theorem works nicely because you can squeeze sine between two manageable numbers. Somebody's asking if we had multiplied by negative x to the 4, we would have changed the signs. Absolutely. This is not a removable discontinuity because the function was actually defined to be 0 at 0. So it's actually continuous. Matt is asking why the sine of infinity does not exist again. Well, I mean, you know the graph of sine. And how would you describe the behavior of sine as the values are getting larger and larger? It's not going towards a specific limit as one value. It's not going towards one value, but rather keeps on going forever. It's not approaching a single value. The limit does not exist. Let's continue this discussion of limits with limits at infinity. Let's give a definition for that. We say the limit as x goes to infinity of f of x is L, right? I mean, this sign business really ties into that. We're asking, what is the behavior of the function as x goes to infinity? Is it approaching a single number? So we say the limit exists and is L if f of x can be made arbitrarily close to L, right? In other words, a function behaves like L by taking x sufficiently large. So again, we're saying that f of x behaves like L for large values. It will come as no surprise that there is an equivalent epsilon delta definition here, which we will not discuss. And even in the definition of continuity, right? Because continuity was defined in terms of limits. There is an epsilon delta definition for continuity as well. Here I have defined. Well, wait, no worries. Back, excellent, good. For those of you who may have missed it, limit as x goes to negative infinity. Similarly, right, the behavior of f for large negative values. Let's illustrate. Limit as x goes to infinity of the function 1 over x. Let's just get a feeling for what is happening to this function as x gets larger and larger. Give me a large number. If you look at the number 100, this is 1 over x. If x is 100, this is the value 1 over 100. Very small number. And if x is larger, like 1,000, this is 1 over 1,000. And you see what's happening, right? As x gets larger and larger, the fraction itself gets smaller and smaller, closer and closer to 0. Similarly, if you're looking at the behavior as x goes to negative infinity of the same function, instead of plugging in positive values, you're just plugging in their negative counterparts. And you're looking at the behavior of this function. If x is negative 100,000, this is negative 1 over 100,000. Very, very small, very close to 0. And if you keep taking larger and larger negative numbers, this whole thing is getting closer and closer to 0. And you can actually generalize this idea. If you have a non-zero number over infinity, or a 1 over infinity, whether it's positive or negative, right? In other words, 1 over a large number, and that number keeps getting larger and larger, you're going to have this scenario happening, right? 1 over plus or minus infinity in the context of limits is 0. This comes as no surprise, because if you cross multiply, right? If you cross multiply, you would get a 1 over 0 is some sort of infinity, a rule which we had seen before in the context of limits. Right? So if 1 over 0 is some sort of infinity, then 1 over some sort of infinity should have been 0, which it exactly is. Now, consider a limit as x goes to infinity Well, Michael is now suggesting 0 times infinity. Shouldn't that be 1? Let's actually not go there, because all I'm suggesting here, Benjamin, is that in the context of limits, a 1 over infinity is going to be 0. Or, as we had seen before, 1 over 0 is some sort of infinity. Only in the context of limits. Right? This idea can be generalized here. That's all I'm saying. However, let me bring your attention to this. Limit as x goes to infinity of x over x. What is that limit? Of course, the x over x can be canceled, and you just get a limit of 1. So the answer here is going to be 1. What I wanted to bring your attention to is that if you just blindly plug in infinity, this had the form infinity over infinity. So in this case, infinity over infinity is 1. But if you change the numerator to 4x, this still has the form infinity over infinity. But of course, in this case, the limit is 4. And if you change it to 14x over x, it still has the form infinity over infinity, but the limit is 14. In other words, what am I trying to suggest here? In the same way that 0 over 0 was an indeterminate form, so is infinity over infinity. And before we leave this, because Michael brought up the interesting question, what if I brought this to the other side? Could we consider, or could we conclude that 1 times infinity, or sorry, that 0 times infinity was 1? I didn't want to go there, but since you have pointed that out, let's convince ourselves that it is not the case by considering this example again. Instead of looking at it as x over x, what if you look at it as x times 1 over x? As x goes to infinity, this goes to infinity, and here, 1 over x, I've rubbed it off now, but we just saw that the 1 over x goes to 0. So this has the form 0 times infinity. Of course, in this case, the x is canceled out, and you just get a limit of 1. But if you change this to a 4, it still has the form infinity times 0. And in this case, the limit's going to be 4 and 14 and so on and so on. So in the same way that infinity over infinity was indeterminate, so is 0 times infinity. Ali is asking if it's x over x, do we say the limit is 1 or it's indeterminate? The limit is going to be 1, but the form infinity over infinity is indeterminate. This just means that you cannot determine what the answer is by knowing it has the form infinity over infinity. Same with 0 over 0, and same with infinity times 0. In the context of limits, these are indeterminate. Let's take some examples. Where did infinity times 0 come from? It came from Michael, which was suggesting, why not just bring this over there? And then could you conclude that 0 times infinity was 1? I didn't want to leave you with the impression that this was the case. So we discussed it. Consider this. As x goes to infinity, let's just plug in infinity, see what's happening. If we blindly plug in, just think of infinity as a very large number and it keeps getting larger and larger. So as x goes to infinity, this goes to infinity. 3 times infinity is infinity, right? 3 times a large number just keeps making it larger and larger. Infinity plus 7 is infinity. And minus 2 over infinity, you see what's happening, right? The fractions are getting smaller and smaller, closer and closer to 0. This limit is 0. Plus minus 2 over infinity. It's the over infinity that's important here. The infinity is on the bottom, so you're getting these fractions which are smaller and smaller, closer and closer to 0. Will it always be 0? In the context of limits, but 1 over some sort of infinity is 0. All right, consider this. What's happening here? If we blindly plug infinity, numerator is going to go to infinity. Denominator, right? Negative infinity squared is infinity times 6 is infinity. Numerator is going to go to infinity. Denominator, negative infinity squared is infinity times 2 is infinity. 9 minus infinity is negative infinity. So in other words, regardless of the plus or minus business, we're looking at an infinity over infinity. An indeterminate form. Something's got to be done. What are we going to do? Right, some work needs to be done here. Well, Michael, we don't even know what a derivative is, so we certainly cannot apply L'Hopital's rule. Instead, we're going to factor. We're going to factor out the issue. The issue is the x squared, which is making everything infinity. Let's factor out an x squared from the numerator. What does that leave us with? 6. If we factor out an x squared, we have 1 over x. And finally, a 5 over x squared. You know, I mean, look, I know some of you are familiar with L'Hopital's rule, and it's a nice and powerful tool. The problem is, it doesn't answer every single question. So you have to be comfortable with these other techniques of evaluating limits. Here, a simple factoring out of an x squared does the trick, because now we can cancel these. And this x goes to negative infinity. The 1 over x, this goes to 1 over infinity, which is 0 in the context of limits. This goes to 0. 5 over x squared, 5 over infinity, is 0. 9 over x squared, 9 over infinity is 0. So these three terms go to 0, leaving you with 6 over minus 2, which is minus 3 as suggested by a few people. How do we do it? Benjamin is asking why we can cancel the x squares. Well, I mean, first we have multiplication, and of course, x squared over x squared is just 1. How do you pull out an x squared from a term that doesn't contain x squared? Convince yourself by multiplying that back out now. X squared times 6 is the 6x squared. X squared times 1 over x, or x squared over x, is just x. And so on and so on. Consider this. Limit as x goes to negative infinity. What's happening? Let's just blindly plug in, see what happens. If we don't have an indeterminate form, we're probably going to be done. But as x goes to negative infinity, u squared goes to infinity. So this is infinity. This is going to be infinity. So infinity times infinity is infinity. And of course, the denominator is infinity as well. So this has the form infinity over infinity. Something's got to be done. This is an indeterminate form. You don't know what the answer is just by knowing infinity over infinity. Let's pull out. Let's pull out a u squared from this term. So what does that leave us with? 1 plus 1 over u squared. Let's pull out a u squared from this term. 2 minus 1 over u squared. And let's pull out a u squared from here. So this is u squared, 1 plus 2 over u squared. The whole thing squared. squared. U squared times U squared is U to the 4. And here, a product raised to the power, you can raise each of the components to that product. And now you've got a U to the 4 over U to the 4. You can cancel these. As U goes to negative infinity, this has the form 1 over infinity, which is 0. This goes to 0, and that goes to 0 as well. Leaving you with a 2 on top and a 1 on bottom, an answer of 2. Very nice. Michael is asking, can't you just ignore everything and just look at the coefficients of the highest powers? Maybe you could have done that in high school. We don't want to be doing that here. You want to justify every step, and this factoring out is of tremendous importance. What happens to the 1 on the numerator? Well, this is 1, this is 2, so the product is 2. 1 times 2. And then 1 squared on the denominator. Yeah. Consider this, and once again, since we're talking about a limit, plug in, see what's happening. As x goes to infinity, this goes to infinity. So numerator goes to infinity. What about denominator? This is infinity. Times 2 is infinity. Minus 1 is infinity. Square root. Again, you're thinking of infinity as very large numbers that keep getting larger and larger without bound. So if you take the square root of a very large number, it's still going to be very large. Infinity over infinity. This still has the form infinity over infinity. An indeterminate form, something's got to be done. What are you going to do? Let's factor out. Let's factor out an x from the numerator. And let's factor out an x squared inside the square root. And the square root of a product is the product of the square roots. And the square root of x squared square root of x squared, what did we say this was? You know what it is. The x cancel out. As x goes to infinity, 3 over x goes to 0. 1 over x squared goes to 0. So we are left with 1 over root 2 as suggested by Sean and Michael. How are we doing? Well, let's do a follow-up question here. And let me ask you, what if we took the same question, but asked for the behavior as x goes to negative infinity? Well, it's funny that Ella would bring that up, because there's actually something wrong there, right? If we do the same thing, because first of all, if you just blindly plug in, you're looking at negative infinity over infinity and indeterminate form. If we do the same process, which seems certainly very reasonable, and square root of x squared, oops, square root of x squared as before is x, and we're in trouble because this gives us the same answer and it's wrong. There's a mistake. What's the mistake? And, well, where's the mistake and what is it? Because this is incorrect. Right? The square root of x squared is not x. Because here there's nothing mentioned. So it's understood to always be positive. No, not two solutions, because it's a function, but, right? There's nothing mentioned, so it's understood to always be positive. So if x is positive, they are equal. But if x isn't positive, if x is negative, right? Square root of negative 1 squared is the square root of 1, which is just 1, right? It's understood to be the positive square root. So no two values. But if x is negative, it's negative of -1. What am I saying? I am saying that the square root of x squared is actually the absolute value of x. Everything is fine when x is positive, right? So when you're looking at the behavior as x goes to infinity, everything was fine, nothing problematic happened here, but here, very much so. You're plugging in negative numbers. In this situation, you're getting a positive result back, whereas here, you're getting a negative number. Something went very wrong from here to there, and what goes wrong is the fact that this is absolute value of x. And you know that absolute value of x is x if x is positive, and negative x if x is negative. And here we are looking at the behavior for large negative numbers. So this is actually negative x negative x times the square root. These cancel out, but you are left with a negative. And as x goes to infinity, this goes to 0. This goes to 0, so you're left with 1 over negative root 2. So be careful. The takeaway here is that the square root of x squared is not x, but absolute value of x. Here in this case, the absolute value of x was still x. So these canceled out nicely, but you have to be careful. So this is a good place to end. We're already way past our stopping time. Thank you all for coming. Practice this. Limits at infinity. And so the limit is positive, or is it both of them? No. As x goes to negative infinity, the answer is -1 over root 2. As x goes to positive infinity, the answer is 1 over root 2. If we had two values, the limit would not have existed, right? If somehow you're getting two different values as x goes to negative infinity, you know the limit is, if the limit exists, it's one value. Very good, folks. You guys have a good one, and I will see you on Wednesday.